Uh, Hello students, in this lecture we will talk about the current challenges in 3D printing, and it's all about maintaining a balance between the different the different aspects like uh, the mechanical properties, then the porosity, then the interconductivity, and board size. All these things are very important in using 3D printing. And this 3D printing is actually a slow process. So not always possible to fabricate any scaffold. If you would like to form a scaffold, it's time consuming. So what people have switched on to simulations to save the time and energy and money, whatever is required. So this it is an alternating tool for predicting the mechanical properties and with different design parameters. So this slowness is the main reason of not using the experimental part of it. Now, and we are mainly using this 3D printing. For example, it's if used in say in bioceramic. Now, first start with the idea of something called an non-linear bending, and it will lead to the instability analysis of the system. And it is mainly useful when you are making a bioceramic with magnetic particle fillers. Like magnetite, for example. So when we are analyzing this, uh, we need to take up some mechanical properties. Like we will first start with something called the maximum rupture strength, and it is given as sigma r, and sigma r is equal to uh, 2p by pi d into t, where p is the tensile strength, this p here, this is the tensile strength, and this is the diameter, and this is t is the thickness of the sample. Now this is actually this equation, this whole equation is actually an approximation. This whole equation is actually an approximation of the main equation. So we take up something called, we consider that the scaffold made is in the form of a disk. Of a disk, and this is called a Brazilian disk. And there is actually a coefficient k associated, and this coefficient is when we take this value as 1, we end up with this maximum rupture strength formula. Now, according to Griffith's criterion, I consider Griffith's criterion for failure. Sigma g is equal to sigma r. So we can write, so this sigma g is equivalent stressed based upon Griffith's energy criterion. So in that case, the value of k turns out to be equal to sigma g divided by 2p by pi d into t. And this is again related to something called from the Poisson's ratio and load displacement. So the elastic modulus E is the elastic modulus, and so this is determined by using a formula given by Wang et al. And it says that the displacement during the experiment, which is taking place in a millimeter, is given as 2 2p divided by pi E into T multiplied by and expression which is root to 1 minus mu, which is the Poisson's ratio, minus natural log of 1 plus 4 by sin squared alpha and multiplied by alpha by sin alpha, where P, as we said, is uniformly distributed applied force, and mu is the Poisson's ratio. So here we get the elastic modulus E.